Hi everyone. In this lecture, we will study null quantification rules. First of all, what it means, null quantification. Null quantification, what it means. Okay, so that we will understand, don't worry. But before that, let's see so far what we have seen. So far, we have seen distributive property of quantifiers. In this distributive property of quantifiers, tell me what we have done. Actually, this is important that you understand distributive properties of quantifiers. Okay, so in these distributive properties of quantifiers, what type of expressions we have seen in these distributive properties? This type of expression we have seen, like for all x, px, or qx. Agree? This type of expression we have seen where this is a predicate, this is a predicate. This type of expression we have seen. Okay, for all x, px, or for all x, qx. Now, in these expressions, notice one thing, that does it depend on x? Tell me. Does it depend on x? Does it depend on x? Yes, these are predicate over variable x. They depend on x, right? Look at only px. Look at only px. Just look at this. Look at px. It depends on x. Look at qx. It depends on x. So that is the reason I can say that this quantifier can affect them, right? This quantifier, it can affect this. This quantifier can affect this. And this quantifier can also affect this because they depend on x. If you notice, just look at the px only. Don't look at universal quant. Don't look at these things. Don't look at these things. Now you tell me, does it depend on x? Does it depend on x? Yes, it depends on x, right? In this, x is the free variable. In this px, x is the free variable. Agree? Look at only px. In this, x is the free variable. That is the reason universal quantifier with variable x will affect it. For example, let's assume that px is x is male. Let's assume qx is x is female. Now you can notice here. Can you notice this x has this x is the free variable here? Agree? This x is also the free variable here. These are the free variables. Now you tell me one thing. If your domain is set of all people, then which expression will be true? If I give you the domain, if I give you domain as set of all people, then tell me which expression will be true? You can easily notice that this expression will be true. This expression will be true, but this expression will be false. This expression will be true. This expression will be false. If your domain is set of all people, then you can notice this expression is true and this expression is false. This example can tell you that this direction is invalid, right? Agree? This example is telling you this direction is invalid. Yes or no? Please tell me. So this example is telling you that this direction, this is invalid. Okay. But tell me one thing. This is very important that here you can notice this is also predicate over variable x. This is also predicate over variable x. In this also x is free. In this also x is free. In this also x is free. Because x is free here, because x is free here, that is the reason this universal quantifier can affect them. That is the reason this universal quantifier can affect. Yes or no? Agree? That is the reason this universal quantifier is affecting them. For example, one more example, let me give you. Like if you have this px, x is prime, and the domain is, let's assume, set of natural numbers. Now you tell me, in this px, x is free or not? In this px, tell me. Yes, x is free. X is free. That is the reason universal quantifier can affect it. That is the reason for all x px. Is this same as px? Is this same as px? Is this same as px? The answer is no. This is not same as px because there is free variable. So this universal quantifier can affect it. This is actually false. This is not same as px. This is actually false. This is a proposition. I can call it proposition. So you can see this is a proposition. Okay. So simple point. Twinkle, don't take empty domain. Never take empty domain. Okay. So anyway, is this point clear? That because this x is free variable, in this predicate, x is free variable. So that is the reason you can notice this universal quantifier can affect. Okay. Now you tell me one more point. If I give you this expression a, in this expression a, I am saying 2 plus 2 equal to 10. And let's assume the domain is a set of natural numbers. Now can I say this is same as a? Now in this a, there is no free variable. Now in this, there is no free x. So can I say this a does not depend on x? This a has nothing to do with x. Independent of x. Does not depend on x. Does not depend on x. So that is the reason this is unaffected by the quantifier for all x. This is completely unaffected by the quantifier for all x. This is also unaffected by there exists x. Okay. Now you tell me one thing. In this expression, this is also affected by universal quantifier. This is also affected by universal quantifier. Okay. So you can see this, they are affected by this universal quantifier. Affected. I can say this is also affected. And this is also affected. And tell me about this. Here also, this is affected, right? Correct. This is also affected by this quantifier. And this is also affected by this quantifier. Right? But tell me, if I replace this with something which is unaffected by quantifier, if I replace this with something which is unaffected by quantifier, like this a, which is unaffected by quantifier. Is this point clear? This a, like for example, this a can be this. This a can be this. So if I replace this a, which is completely unaffected by the quantifier, which is completely unaffected by this quantifier, then this type of expression we will call null quantification. Is this clear? This type of expression, we call them null quantification. We call this type of expression null quantification. Why? Null quantification means this is not affected by for all x. Is this point clear? What is null quantification? Tell me. See, this a can be this. For example, this a can be this. This a is unaffected by the quantifier. Yes or no? You can notice this a. This does not depend on x. So for all x a, that will be same as a. This we have already seen. In this a, there is no free variable x. So this a is completely unaffected by for all x. This a is completely unaffected by there exists x. So I can say this a is unaffected by for all x, there exists x. So that is the reason. In your expression, if you have this a, this is unaffected by for all x. So this type of expression is called null quantification. Please tell me, is this point clear? What is null quantification? Is this point clear? What is null quantification? The name itself is telling you. Let me know. The name itself is telling you null quantification means something is not quantified. Null quantification means something is not quantified. Okay, something is not quantified means I can say, for example, here I can say null quantification means if I write this expression, for all x, px implies a, where this a is completely unaffected by for all x, where this a, that is unaffected by for all x, unaffected by for all x. So this type of expression will be called null quantification. Is this point clear? Please tell me. Don't worry about the remaining things. Everything will come slow by one by one. Please tell me, is this point clear? Is this point clear? What is null quantification? This A is completely unaffected by 4 whole x. So that is the reason this type of expression is called null quantification. Null means nothing. Okay, null quantification means this part, I can say this part is unaffected by 4 all x. So when you have this part which is unaffected by 4 all x, this type of expression we call them null quantification. Now tell me one more thing. When can you say that this is unaffected by 4 all x? Simple point. A is unaffected by 4 all x. When can you say this? Unaffected by 4 all x, or there exists x. Tell me, when can you say this? When can I say that this is unaffected by them? When can you say that this is unaffected by them? It simply means A has no free variable x. A has no free x. Agree? It simply means A has no free x. Is this point clear to everyone? This is important. That if this is completely unaffected by 4 all x, there exists x, then it simply means that A has no free x. And if A has no free x, then can I say this? A has no free x. Then I can say this. So yeah, that is correct. This is all you need to understand. So this type of expression will be called null quantification. Means I can say, if you have this expression, let's assume you have quantifier. So let's assume you have some quantifier. This quantifier is, let's assume, some pi. Either this quantifier can be for all, or this quantifier can be there exist. And let's assume you have some operator hash. This operator can be what? Tell me. This operator can be, for example, conjunction, disjunction, implication, by implication. So these operators, exclusive or, NAND, NOR, these operators. Now, what is null quantification? What is the definition of null quantification? Tell me, what is the definition of null quantification? Null quantification means some part is unaffected by the quantifier. Right? Some part is unaffected by quantifier. Okay, some part is unaffected by quantifier. Or I can say the same line. How can I rewrite the same line? This same line, how can I rewrite this same statement by the quantifier by the quantifier pi x? Now tell me. So this pi either can be for all, or this can be there exist. Now I am saying that some part is completely unaffected by this quantifier. This same statement, how can I rewrite? Tell me, how can I rewrite this same statement? I can rewrite like this, that some part has no free x. Isn't it? Some part has no free variable x. Agree? So far, everything is clear? That some part has no free variable x. This type of expression is called null quantification. Okay? Now, after this point, what you need to remember? Something. So this type of expression, for example, I can write, like I can say for all x, px and a. This expression is null quantification. Here, this a has no free x. This a has no free variable x. Similarly, for example, I can write like this, there exists x, a implies px. Here also, this a has no free variable x. So this type of expressions are called null quantification. So here, this expression is like null quantification. Okay, means some part has no free variable x. This is important. Clear? some part has no free variable x. This type of expressions will be called null quantification. So that's it. Null quantification means some expression isn't affected by quantifier. And this same statement I can rewrite. This same statement I can rewrite as some part has no free variable x. Has no free variable x. Simple. Okay. Now let's move on. Now you already remember that what is if this a has no free variable x. Let's assume this a, this has no free x. If this has no free x, then you already know what is 4 all x a. Tell me, what is 4 all x a? That is same as a. And what is there exist x a? That is same as a. Because this a has no free x. There is no free variable x here. So this is completely unaffected by 4 all x, there exist x. Now, if I give you this expression, so if a does not have any free variable x, then if I give you this expression, is this valid? Think about it. I am giving you one expression. For all x, px or a. For all x, px or a. Okay. Now, do you remember that normally what happens is this, are they equivalent? Like if this a has free variable x, if this a has a free variable x, if this a has free variable x, then can I say they are equivalent? Then can I say they are equivalent? Tell me. If this a has free variable x, here you can notice this also has free variable x, this also has free variable x. So in this situation, they are not equivalent, correct? Okay. But now what I have done, now I am doing this, that a has no free variable x. So a does not depend on x. If a has no free variable x, should I write this? If a has no free x, then what should I write? Should I write like this or should I write like this? Tell me. Should I write like this or should I write like this? This is wrong. This is correct. Because a has no free x. Okay. Now let's move on. Now you tell me, are they equivalent? Now things are changing. Now things are changing, remember. Because now this a does not depend on x. Now things are changing. Here this a independent of x. This is independent of for all x. Remember this a, it has no free x. So this a is completely independent of for all x. Because this is completely independent of for all x. Okay, this does not get affected by this for all x. So can I simply create two cases? I can simply create two cases that either this will be true or this will be false. I can create two cases from this universal quantifier point of view. This a does not depend on this for all x. This a does not get affected by this for all x. So from this universal quantifier point of view, I can simply create two cases that either you will be false or you will be true. I cannot affect you. See what this universal quantifier is thinking. See the thought process of this universal quantifier. What this universal quantifier is thinking? This is thinking that I cannot affect a. Yes or no? I cannot affect this a. This universal quantifier is thinking I cannot affect this a. So simply I can create two cases that either you will be true or you will be false. So simply create two cases. So simply create two cases. One case where you consider where a is true, this possibility you consider, and one case, this possibility you consider. So these two possibility you consider and then solve the question. So you consider these two possibility and then you solve the question. Simple. Okay. So now let's solve this question by considering these two possibilities. And tell me, when can you say something will be valid? Valid means always true. So always true means in both the cases it must be true. Agree? So valid is always true. It simply means in all cases it must be true. In all cases it must be true. In some case, if it is not true, then in some case, if it is not true, then invalid. So simple idea. Valid means always true. Means in all cases this must be true. Okay. Now let's solve this question very easily. You can solve now. So just create two cases. Let's call this LHS. Let's call this RHS. Two cases you create to solve this question. To check this equivalence, you create two cases. What is case one? Tell me case one. You create two cases. Case one, A true. Case two, A false. In this case, what is LHS? In this case, what is LHS? When A is true. In this case, when A is true, then this LHS is simply true. A is true. A is true. True or this, it will always be true. A is true. So here you can notice if your PX or true, here you can notice that this is always going to be true for all elements. This is always going to be true for every element in domain. Element in domain. Simple. This will always be true for every element in the domain. This is always going to be true for every element in the domain. So now I can simply say that LHS will be definitely true. What about RHS? What about this RHS? This is some proposition. Is this proposition for all x px? Is this proposition? Yes, this is proposition. And this is true. True or something that is true. So easily you can notice this is also true. Are they equivalent? Yes, they are equivalent. So can I say this is equivalent? Can I say this equivalence is valid? No, I have to check this second case also. This case also I should check. Now in this case, you tell me what is LHS? What is LHS in this case? When A is false, then false or P, that is P. So LHS will be for all x px. And what is RHS? RHS is also for all x px. Are they equivalent? Yes, they are also equivalent. Now can I say they are equivalent? Yes. Now I can say in both the cases they are equivalent. So ultimately they are equivalent. Clear? Let me know. So what we have done, remember, this is what we have done. Conclusion. This is the conclusion that if you have this expression for all x px or qx, we know this is not equivalent to for all x px or for all x qx. But we have seen that if some part has no free variable x, like if this A has no free x, this A has no free x, then in this situation, this is actually equivalent to for all x px or A. Understood? Is this clear? And these proofs are very easy. So ultimately, checking validity. If you want to check the validity, this checking validity, when A does not have free variable x, then all you have to do, just create two cases, A true, A false. Valid means in all the cases it should be true. Invalid means in some case invalid, then expression is invalid. This is the simple method. Now let's solve the questions. Let's solve this question. So first of all, in this question, you can notice the question is based on null quantification from the Kenneth Rosen book. This is the question number 46 from this book, Kenneth Rosen. And read this statement. Null quantification. Null quantification means when a quantified variable does not appear in a part of a statement. Agree? This we have seen that this is the null quantification. Correct? We have already seen this is null quantification means when a quantified variable does not appear in a part of a statement. Like you can see, this a is not a free variable in this x is not a free variable in a. This x, this is not a free variable in a. This is not a free variable in a. See, this is the quantified variable, but this does not appear in a. Twinkle, this quantified variable does not appear in a. This quantified variable, this is the quantified variable, this does not appear in this a. Is this clear? Let me know. The wording is clear, the statement is clear that this quantified variable does not appear in a. Or I can say this quantified variable is not a free variable in a. This variable is not a free variable in a. In this a, there is no free variable x. Okay, now let's prove them. So this we have already done, right? This part A we have already done. Now let's see the part B. The part B is saying there exists x, px or a. Is this same as there exists x px or a? Are they same? This is very easy to prove. Let's see, are they same? Again, what you will do? Tell me what you will do. You will create two cases. Case 1, where a is true, and case 2, where a is false. You will create two cases because this a has no free variable x. Has no free variable x. So now you can create two cases. In the case 1, what will happen? Tell me. In the case 1, what is LHS? This LHS, let's call this LHS. What is LHS? Tell me. When a is true, then this expression will always be true. So this LHS is true. Because this a is true. True or px. This will always be true for all the elements in the domain. For every element in the domain, this will always be true. This will be true for every element in the domain. So this LHS is true. What about RHS? This is true. True or anything, that is true. So in this case, they are equivalent. What about case 2? In case 2, what is LHS? A is false. A is false, so LHS is there exists x px. And RHS also will be there exists x px. Again, they are equivalent. So can I simply say that this is a valid? Yes or no? These questions are much easier than those distribution property questions. These questions are very easy if you notice. Much easier than the distribution property questions. So can you try this question? This question also from Kenneth Rosen book, question number 47. So let's see this question. In this question also you can notice this statement is given. Read this statement. This statement tells you what? This statement tells you what? Tell me, this statement tells you what? That this is null quantification. This statement tells you that this is null quantification, right? Okay. Now, so let's see the part A. How will you do the part A? The part A is for all x, px and a is the same as for all x, px and a. Are they same? These two. Let's see. So how will you do? Let's call this LHS. Let's call this RHS. Again, you can simply create two cases. One case where A is true, another case where A is false. Okay. One case where A is true, another case where A is false. Why I cannot create cases for P? Why I cannot create cases for P like P true, P false? Tell me, what is the reason I cannot create cases for P, P true, P false? Because that is actually affected by this quantifier. This is actually affected by this quantifier, right? This Px, this is actually affected by this quantifier because this Px has free variable x. Look at Px. Don't look at other things. Look at Px only. If you look at Px only, then this has free variable x. So this is affected by the universal quantifier. Anyway, this A is not affected by the universal quantifier. This A has no free x. So this is completely unaffected by this universal quantifier. Now you tell me, in this case, what is LHS? When A is true, then what is LHS? LHS is for all x Px. And what is RHS? A is true. So RHS is also for all x Px. Are they equivalent? Yes. What about the next? If A is false, then what is LHS? LHS will be false because A is false. So for every element, this will be false. For every element, this is going to be false. In the domain, for every element, this is going to be false. What about RHS? A is false. False and anything, that is simply false. So these are also equivalent. So can I say this is valid? Yeah, that is valid. So these are equivalent. What about the part B? What about this part B? Again, the same thing. This A has no free x. This is completely unaffected by the quantifier, completely unaffected by there exist x. So you can simply create two cases. In one case, A true. In another case, A false. Simply create two cases. Now again you tell me, when A is true, what is LHS? What is LHS? This LHS, when A is true, this will be there exist x Px. And when A is false, when A is true, then what is RHS? RHS is also there exist x Px. What about when A is false? If A is false, if this is false, then for every element, this will be false. For every element in the domain, this will be false. For every element in the domain, this is going to be false. So easily I can say this LHS will be false. And what will be RHS? A is false. False and anything that is false. So this is also equivalent. Here also equivalent. So can I say this is also valid? These questions are very easy. Agree? Much easier. Let's move on. So far, what we have seen? So far, these points we have seen that this universal quantifier, whether you put and or, Px and A, this is equivalent to for all x Px and A. Right? Similarly, here you can put or also. This here you can put or also, that is fine. So I can say that you can put hash. You can put hash, and here this hash can be and, or this hash can be or. Okay, this hash can be and or. Similarly, remember there exists x Px hash A, that is same as there exists x Px hash A. Here also you can notice this hash can be either conjunction or disjunction. Correct? Agree? So now let's see the next question. Interesting question are coming. Some interesting questions are coming. So solve this question, try this question. This is question number 48 from the Kenneth Rosen. We have already done 46, 47. 46 done, 47 done. This is question number 48. Let's try this. Again, you can notice this line. What this line tells you? X does not appear as the free variable in A. What this line tells you? This line tells you that for all x A, that is same as A, there exists x A that is same as A. Okay. Now you tell me, are they valid? The first one, for all x A implies Px. Is this same as A implies for all x Px? Are they same? Again, very easily, you can create two cases. Case 1, A true. Case 2, A false. Just create two cases. Now, if you create two cases, then when A is true, then what is LHS? And what is RHS? Tell me. A is true. A is true. Tell me, true implies M. What is that? True implies M. What is that? That will be same as M. True implies M is same as M. So here you can notice that if this A is true, then you can simply write it for all x Px. Here also, if A is true, then you can simply write it for all x Px. So these are equivalent. If A is false, then what is LHS? A is false. This is false. False implies anything is true. So this LHS will be true. This RHS will also be true. So they are again equivalent. So can I say this is valid? Yes, they are equivalent. What about the next one? If I put existential quantifier here, if I put this existential quantifier, you can check this is also valid. Okay, this is also valid. This will also be valid. So you can easily notice that this is also valid. Again, you can just create two cases. When A is false, then what are LHS, RHS? What is LHS? What is RHS when A is false? So when A is false, then remember this point that false implies anything that is a true. False implies anything is true. So if A is false, then simply I can say this LHS is true, RHS is also true. So they are equivalent. What about the second case? When A is true, remember, true implies M, that is same as M. I can say that in this case, your LHS will be there exist x Px, and your RHS, that also will be there exist x Px. Are they equivalent? Yes. So they are also equivalent. So far what we have seen, this is the conclusion. We have seen that this, and we have seen for all x, A implies Px is equivalent to A implies for all x Px. So far everything is clear. These questions are very easy, right? Okay. The more the easier the questions, the more they are boring. Like, agree? These questions are actually very easy, very, very, very easy. But these are slowly you are getting bored. Slowly you are getting bored, right? In the distributive property of quantifier, in those questions, you did not get bored. Those questions were not boring. Okay. Whether you can solve them or you don't solve them, whether you get the correct answer or not, but those questions are not boring. But so if you are bored, then some interesting points would come. Some interesting questions would come. So let's see this interesting question. So we have seen, remember, if you have this A implies Px, this A implies Px, A implies Px, this is distributive, right? When you have A implies Px, this is completely distributive. When you have A implies Px, this is completely distributive. Now let's see what happens when your Px implies A. What happens when your Px implies A? So let's see this question. This is question number 49 from Kenneth Rosen book. What we have done? 46 done, 47 done, 48 done. This is the 49 question. Let's solve it also. Let's do it also. So tell me. So here X does not occur as the free variable in A. So that simply tells you that this is null quantification. Okay, and when you have null quantification, then you can simply create two cases, either A true or A false. You can just create two cases, case 1, case 2. Simply create two cases. Okay, so let's solve this question. Interesting things will come. Now it will come. For all X, now we are changing this. Now we are putting this A here. Is this equivalent to for all X Px implies A? Are they equivalent? Are they equivalent? Are they equivalent? Tell me. These two, are they equivalent? So let's create two cases. Again, case 1, A true. Case 2, A false. In case 1, what will happen? In case 1, what will be LHS? A is true. So I told you M implies true. That is always true. So here I can say LHS will be true. What about RHS? A is true. RHS also will be true. So here they are equivalent. Okay. What about this case? A is false. What about LHS? Remember, if you have M implies false, that is same as M negation. M negation, right? So here, what is LHS? Px implies false. That will be like for all X negation Px. And RHS is, what will be RHS? RHS will be negation for all X Px. That is same as there exists X negation Px. Are they equivalent? Are they equivalent? These two, LHS, RHS, they are not equivalent, correct? These two are not equivalent. But who implies whom? So, but who implies whom? LHS implies RHS or RHS implies LHS? They are not equivalent. This, they are not equivalent. But you can say that this LHS implies RHS, right? LHS implies RHS because for everyone P is false, then definitely for someone P is false, right? For everyone P is false, then definitely for someone P is false. So I can say LHS implies RHS. In this question, it has become something interesting that here actually LHS will imply RHS. Actually, this implies this. So this you can say, yeah, this implication is correct, remember. This implication is correct, but this implication is wrong. Understood? Tell me, understood? Is this point clear? See, very simple. This LHS implies RHS, right? Here they are equivalent. In this case, they are equivalent. See, in this case, you don't have to worry. In this case, they are equivalent. But in this case, you can easily notice that LHS implies RHS. This LHS, it implies RHS. Because LHS is saying for everyone P is false. RHS is saying for at least one person P is false. And you know that if this happens, then definitely this will happen. So I can say LHS implies RHS. Understood this point? Something interesting. This point is clear. Let's see the part B. What if I put existential quantifier here? Now are they equivalent? Again, they are not equivalent. You can see the case 1. What is the case 1? Again, A true. And what is case 2? Case 2, A false. So tell me, when A is true, then what your LHS will be? When A is true. When this A is true, then LHS will be simply true. Because if this is true, then for every element, this will be true. For every element in the domain, this will be true. So I can simply say that LHS will be true. What about RHS? If this is true, anything implies true, that is true. So here also they are equivalent. What about case 2? In case 2, what is LHS? In case 2, LHS will be there exists X, negation PX, and RHS will be negation of there exists X PX. That is same as for all X negation PX. Are they equivalent? Are they equivalent? No. Who implies whom? Who implies whom? RHS implies LHS. RHS implies LHS. So they are not equivalent. They are not equivalent, but who implies whom? So here I can say RHS implies LHS. So this direction is wrong, but this direction is correct. Do you agree that all these questions are actually very simple? Whatever direction, you can easily notice, you can easily check. Whatever question I give you from the null quantification, these are very easy. Whatever I do, whatever I give you. So what we have done, let's see the interesting point. The interesting point is this. What we have seen is that if you have this situation, like for all X, A implies PX, then here I can jump. Then this universal quantifier can jump. This universal quantifier can jump, right? This universal quantifier can jump. Yes or no? Clear? Do you agree? We have already seen this. Yes or no? But when this universal quantifier cannot jump, when you have this Px implies A, now this universal quantifier cannot jump. Now this universal quantifier cannot jump. Agree? We have seen this point also. We have seen this point also. Okay? Yes or no? We have seen this point also, this point also. In the exam, if this question comes, can you prove it? If you forget, let's assume you forgot. You forgot. For a moment, assume you don't remember anything. Can you prove it easily? Yes. During the exam, you can prove it very easily. You can prove it. But let me tell you something interesting story here. Have you seen this type of situation in your general life? That basically here this can jump here. This universal quantifier can jump here when A is here. But this universal quantifier cannot jump when this Px is here. How to remember this? Actually, you don't have to remember. One thing you don't have to remember, you can prove it immediately. Agree? Yes, you don't have to remember, but you can prove it immediately. You can prove it. But I just want to tell you one superstition. Okay, there is a superstition in I don't know about the other state, but in Rajasthan there is a superstition. In Rajasthan, we have this superstition that like if someone is, let's assume someone is lying here. Okay, this person. And let's assume this is the sibling. So let's assume A comma B, they are, let's assume, siblings. Okay, and let's assume this A is lying. Okay, so this is like lying here. Okay, lying down. Okay, whatever. Now, so what people say, the mother will say, if this B wants to go here, then what this mother will say? Then this mother will say immediately, you don't do this, else height will not increase for A. Okay, so basically, don't cross, something like this. person, else their height will not increase. Don't cross over a person, else their height will not increase. Have you heard about this? This superstition, have you heard about? Their height will not increase or something. Something like this. Anyone here who has heard about this type of superstition? Okay. Anyway, you maybe okay. So anyway, the point is this: don't cross over a person. Okay, this type of superstition is there. Actually, the similar thing also happening here also. See, can I say that this A does not have any feeling for universal quantifier for all x? This A does not have any feeling for this quantifier. Also, there is one Bollywood dialogue. What is that? There is a very frequent dialogue in the Bollywood. What is that? अगर जाना है तो मेरी लाश के ऊपर से जाना पड़ेगा. Okay? There is a very famous dialogue. If you want to go, then go over my dead body. Something like that. Yes. This you definitely have heard about it, right? Then go over my dead body. This dialogue, you have heard about this, right? If you want to go over my dead body. Okay. So basically, don't go. If someone is not dead, then don't go over them. Okay. So this dialogue you have seen. If you want to go over my dead body. Okay. So this dialogue you may have seen. Now here you can notice, can I say this person is dead for this person? Tell me, can I say this person is dead for this person? Can I say this A has no feelings for all x? A has no feelings. A is dead for all x. I can simply say that A is dead. And because it is already dead, so you can cross, right? Yes or no? Because it is already dead. It is already dead. It is already dead. So no problem. So you can cross. Okay. So anyway, like this, you can remember, but you don't have to remember. The one thing I want to tell you, you don't have to remember, but this is just a small, when I saw this expression for the first time, let me tell you, when I was preparing for the GATE exam and I saw these two expressions, at that time, immediately this dialogue came in my mind. So that is the reason I'm telling you. This dialogue came in my mind that if you want to go, then go over my dead body. See here. So this A is already dead. This A is dead for 4LX. So you can jump. So there is no problem. You can jump. So no problem. You can jump. But here this is alive, right? Can I say this is alive? This is alive for 4LX. Yes or no? Can I say this is alive for all x? So you cannot jump. So don't jump. Okay, anyway. So, but you don't have to remember. You can just prove them. And the same thing happens here also. Same thing happens for the existential quantifier also. So this, there exists x. A implies px. क्या बोलते हो? Jump करवा दें? Tell me. Can we jump? Can we jump? This is already a dead body. So can we jump? Yes. Okay, so like this. A implies there exists x px. Can you prove them? Tell me. Do you need to remember like this? Do you need to remember like this? Like this, do you need to remember? No. You can prove. I'm again telling you, you can prove. Okay, so like someone is asking, Chinmay, can you prove? You don't have to remember. Can you prove? Just tell me this point. Chinmay. Yes. So that matters, right? You can prove that. That's all that matters. So you can prove it. So the point is that here you can jump. And similarly, what about this? There exists x. Px implies A. Can you jump? Can you jump? So here you cannot jump. Okay. So anyway, this applies for, yeah, this is same for universal quantifier also. The same thing happens for universal quantifier and for existential quantifier. Okay. One more point. This we here you can notice that for all x, if I say px implies a, this is not equivalent to for all x px implies a. This we have seen, correct? Correct. This we have seen. But actually this for all x px implies a, this is actually equivalent to there exists x px implies a. Can you prove it? Can you prove it? Tell me. This is actually equivalent to, can you prove it? Try this. Try to prove it. All of you, try to prove it. So very simple. If you want, you can prove it by case method. This is like px implies a. Is this equivalent to there exists x px implies a? Are they equivalent? You can easily prove. Just take two cases. You can easily prove it. Just take two cases. Consider case 1. Again, case 1 a true. And consider case 2. Case 2 a false. So tell me, in this case, what will happen? What is LHS in this case? LHS, RHS both are true. When A is true, then LHS, RHS both are true. In case 2, what is LHS? In case 2, what is LHS? When A is false, then LHS is for all implies for all x negation px. And what is RHS? RHS is negation there exists x px. And that is same as for all x negation px. So they are equivalent. Hence proved. So very easy to prove. In the null quantification, will you remember anything? Will you remember anything in null quantification? Whatever question comes, you can immediately solve it. Let's see another method. Let's see another. There is one more method. See, can I say that this is same as for all x px bar or a? Yes or no? This is same as for all x px bar or a. And that is same as for all x px bar or a. And that is same as negation there exists x px or a. Right? Yes or no? See, this is same as this. This is same as this. This is same as this. And finally, what this is same as? This is same as there exists x px implies a. So we got this. Correct? This is another way. Which do you like more? Like this method? Will you do using this method? Or will you can just simply do using this? I think this is also very good. This by case is actually better. You don't have to put this much brain. Okay, that you write this like this, then you write this like this, then you write this like this. You don't have to do this. Okay, you are using too much brain here. So that you don't have to do. Just simply create a true, a false. Two cases you create, that's it. Okay. And similarly, remember, similarly you can also prove this. There exists x, px implies a. We know this is not equivalent to there exists x, px implies a, right? This we have already seen that they are not equivalent. But actually this is equivalent. There exists x, px implies a. This is actually equivalent to for all x px implies a. This is actually equivalent to for all x implies a. Can you prove it? Are you confident that you can prove it? So I leave it up to you. You can do it. So just prove it. Okay. So let's move on. So that's it. Now you can solve this question on null quantification. GATE 2020 question, latest question. GATE 2020, this latest question you can solve on null quantification. On null quantification. This question you can easily solve. In this question, how many options? 4 options you have to do. Okay. Why this question is based on null quantification? Why this question is based on null quantification? Who told you that this question is based on null quantification? Because W is a predicate formula without any occurrence of X. So this is this is telling you null quantification. Before we solve this question, let me tell you one thing. This question came in this year, right? 2020. This question came in this year. Before this year, there was no question based on null quantification. So let me tell you, during my preparation, what was happening. I prepared for the GATE exam in 2017. Okay. This was the time I prepared for GATE exam. In 2017-18, I prepared. Okay. So like this was the duration, 2017-18. Okay. And at that time, let me tell you, at that time, there was no question in the GATE exam. This is the only question in the GATE exam on null quantification. Is this clear? This is the only question in the GATE exam in the last 40 years. This is the only question based on null quantification. Only question on null quantification. Remember, this is the only one question in GATE on null quantification. So when I was preparing for the GATE exam, what people were thinking, tell me? Just think about it. There was no question on this concept at that time. In the GATE exam, there was no question on this concept. So nobody studied. Let me tell you, no one taught. Okay, no one taught this concept in any coaching institute. Also, no one studied. And finally, and you can see, this was when I was GATE aspirant. At that time, I wrote this answer on GATEOverflow on null quantification. So you can see, this was even edited in 2018. I re-edited this, but you can notice at that time, remember the question came, the GATE question came in 2020. And I wrote this answer when I was GATE aspirant. This answer I wrote with proof. With proof, actually, if you see, you can see the complete proof. This is not the complete answer. The answer is almost 2 pages long. Almost 2 pages long answer I wrote. With proof. And when I wrote this answer, at that time in the GATE exam, there was no question. You can see. But finally in 2020, this question came. In GATE 2020, this question came. Okay. So one thing I want to tell you, this is something that I want to tell you. What many students do, when we teach you some concept, then some students will ask, sir, ye concept syllabus mein hai kya? Is this in the syllabus? Because there is no question on this concept. Let me tell you one thing. We don't teach you after seeing the GATE questions. See, there are 2 ways of teaching. Either you teach the complete syllabus. You don't worry about whether this question came in GATE or not. You just teach the complete syllabus. Another way is you see the GATE questions, and based on the GATE questions, you teach the syllabus. We do the first one. Okay. So that is the reason. Sometimes it will happen. Some concept we will teach you from which in the GATE exam no question has come. But still we will teach you. Because it is possible that some question can come in future. Like this question, this particular null quantification question. Till 2019, there was no question on null quantification in the GATE exam. No question, not a single question. Till 2019. Okay. But in 2020, this question came. And you can see, this is my particular habit, not only about as a teacher, not as a teacher, but as a student also. I always cover the complete syllabus. So when I was GATE aspirant, at that time, I have wrote this null quantification answer. Also, let me tell you, you can see my answers on pumping lemma. In theory of computation, there is a concept, pumping lemma. On pumping lemma, till 2018, there was no question. Till 2018, 2018 tak, till 2018, there was no question on pumping lemma. So no student studied, no teacher taught. But you can see my answers on pumping lemma on GATEOverflow. Have you seen? More than 30 answers on pumping lemma on GATEOverflow. I have written very long answers with complete detail. And let me tell you, finally, in 2019, this question came. Pumping lemma question came in 2019. Okay. So anyway, the final point is we teach you based on the syllabus. So don't worry that, sir, you are teaching this concept, but there is no GATE question on this concept. Why are you teaching this concept? Because there is no GATE question on this concept. So don't do that. We will teach you the concepts from the syllabus. We are not teaching you the concept because the question has come in the GATE exam. Okay. Is this clear? So please understand that sometimes we will teach you some concept based on which no question has come in GATE exam, but still we will teach you because we believe that it is in the syllabus and it can come in the GATE exam. Maybe next year, maybe in 24, 25, 26, 2030. I don't know. Okay. So anyway, so let's move on. So tell me the answer for this question now. What is the answer here? You can solve this question now very easily. This is the predicate formula. So this is null quantifier. So this is correct. What about the second one? The second one is also correct. We have already proved it. What about the third one? Sorry, the question is asking not logically valid. The question is asking not logically valid. So this is actually valid. This is also valid. What about the next? This is invalid. What about this one? This is valid. So this is a valid, I can say. So the answer will be this. Okay, this is the answer. And you can prove it. Let's assume that in the GATE exam, you see this question and you don't remember. Then what you can do? You don't remember. Then what you can do? Just take W false, W true. Okay. So you can easily do this in the GATE exam. Actually, you don't even have to spend time. See what you can do. Let me tell you in the GATE exam, what you can do. You can quickly do this. And this was the year when I got 53 rank. And this is the reason. These type of questions are the reason. This type of questions. Because this type of questions, many students, they cannot solve. Why? Because till 2020, no one taught this concept. No one studied this concept. No student studied, no teacher taught. So when in 2020 this question came, then many students, they could not do this. They could not solve it. And this was a 2-mark question. And do you agree that this was easy 2 marks? Can I say these are easy 2 marks? Very easy 2 marks, right? What you can do, you can simply create 2 cases like W false, W true. 2 cases you can create. Now you can just simply create. What about option A? In option A, so tell me, what is LHS when W false? In option A, what is LHS? Tell me. What is RHS? Tell me quickly. In LHS, if W is false, then LHS will be 4 all x px and RHS will be 4 all x px. And when W is true, then what will happen? In option A, what is LHS? I am checking for option A. So the LHS will be, when W is true, then LHS will be true and RHS will be true. So you can easily notice that A is actually valid. Okay, A is actually valid. So you can note this A, this option A, this is actually valid. And similarly, you can do all the remaining. For example, you can do the option C. Tell me for option C, when W is false, then what is LHS? What is RHS? What is LHS? If W is false, then that is 4 all x negation px. And what is RHS? That is there exist x negation px. So they are definitely not equivalent. These two people, they are definitely not equivalent. Okay, so here you can stop and you can say they are not equivalent. When W is false, so you can easily notice this is invalid. So very easily, all these questions you can solve. Anyway, let's move on. So these were easy 2 marks. In this question, I did not spend even, I think, 5 seconds also. I remember in 2020, when I was giving the GATE exam, in this question, I spent hardly 5 seconds. I did not even read the question properly because I knew that, yeah, finally, I saw this line and immediately I got to know, okay, this is null quantification. Okay, so I did not prove it. The reason is simple, because I already knew. I already knew the answer. If you notice, this is your question 46 of Kenneth Rosen. Let me tell you, this is question 46 of Kenneth Rosen. This is question 47 of Kenneth Rosen. This is question 48 of Kenneth Rosen. 49. This is question 49 of, sorry, 48, right? Yeah. This is question 48 of Kenneth Rosen. And this is question 49 of Kenneth Rosen. They did not even change the options. You can check it out. Today you can check it out. Kenneth Rosen, this is question 46, 47, 48, 49. And all of them we have done. Now, if anyone asks you, why GoClasses follows standard resources, why we are solving standard questions, why we are giving standard questions in the test series, why we are giving standard questions in the weekly quizzes, you can tell the answer. You can show them this question. Okay. And you check it out. Today you check it out. This Kenneth Rosen book, you check it out. You can see this will be question 46, 47, 48, 49. Okay. Anyway, let's move on. So you can easily see. So this is the null quantification we have already seen. Now, just one final topic is remaining, that is arguments in first order logic. This we will study in some other live class, some other day. Okay. On this also, only one question is there in the GATE exam. On this concept, there is only single question, only one question in the GATE exam. But this is also very easy topic. So we will study this in some other live class. Okay. This is the last topic. Actually, let me tell you one thing. All the topics that are remaining in first order logic is actually complete. It is actually complete, let me tell you. But what we are doing, for example, this topic is remaining. This argument topic is remaining. On this argument topic, actually argument in first order logic, this topic is remaining. On this topic, there is only one question in GATE exam. But still, that does not matter. See, this topic is actually very good, very easy. So we will study this. There is a concept model in first order logic. In this, there are 2 questions in GATE exam. Okay. And there is a concept tautology. Tautology in first order logic. There is 1 question in the GATE exam. Let me tell you, in first order logic, these are not same. Okay. In first order logic, valid is not same as tautology. Is this clear? In first order logic, they are not same. So tautology is different. Valid is different. Valid we have seen. Agree? This valid we have already seen. What is valid? That we have already seen. But this tautology is also there. So these topics, these 2 topics I will put today. I will upload today. I will upload them today, and these will be optional. I will put them in the optional category. Optional means these are optional to watch. Okay. So these 2 lectures, these are optional to watch. If you don't watch, that is also fine. Okay. So these will be optional. But anyway, I will upload. The complete lectures I will upload. This complete lecture with practice I will upload. This complete lecture with practice I will upload. So both these topics I will upload, but I will upload in this category, optional. So you can study these, but you don't have to worry about these. Is this clear? You can study these topics, this topic you can study, but you don't have to worry about them. Okay. So anyway, so that's it. Okay. Yeah. Anyone has any doubt? Let me know. So first order logic is complete. Only these, you can see these small topics are there. And one more thing I just want to tell you, these two topics will be optional. And this we will study in some live class. And everything else we have already seen. The complete coverage. Now you can solve the first order logic questions. Apart from these I will upload. Once I upload, then you can solve these questions also. Okay. So now you can solve the gate questions of first order logic. First order logic, gate PYQs, start solving. Okay. Okay. Thank you, everyone. Anyone has any doubt? Any doubt? Null quantification is clear. Simple topic. A true, A false. Simple topic. Null quantification. Okay. And weekly quiz you can attempt. Please attempt the weekly quiz. Attempt weekly quiz 10. This also you attempt. Some good questions are there. It is not very hard. This is a decent quiz. I can say the level is, level is not complicated. Level is, I can say simple level, but the questions are very good. Variety of questions are there. Okay, so you can try this. And also this test one you can upload. This test one in test series, this also you try. This test one in Go Classes test series. Anyone attempted this? In this, there are some beautiful questions. Did you attempt this test one? Test one in the Go Classes test series. Test one. Discrete mathematics test one. So you try this also. Okay. Okay. Thank you, everyone.